All right, good morning, ladies and gentlemen. Today we are going to go over Calc Review 17, but actually I'm only going to cover Part D from each problem because these were the ones that were asked about mostly, and I think the other problems can be found, at least similar solutions can be found in yesterday's video. So, Part D, find the rate at which the volume of water in the pool is increasing at time t equals 8 hours. How fast is the water level in the pool rising at t equals 8 hours? Indicate units of measure on both answers. Okay, so there are two parts to this question. One of them deals with rate of change in volume. The other one deals with how fast, so it's talking about a rate of water level in the pool. So this is going to be a related rate problem. Why? Because, well, it turns out that volume is related to the water level, which is H in this case. Now, one nice thing about this problem is since the pool is a cylinder, that means R is constant. And so when we differentiate, dr dt is just 0, so we can actually just plug 12 in for R, right? Because R is not changing with time. The only items that are changing with time in this equation will be volume and height of water. So for that reason, I'm going to rewrite this expression as V equals pi times 12 squared times H, or of course, V equals 144 pi H. All right. Now we want rate of volume and rate of water level. And so now I'm going to differentiate. Both of these are functions of time. So I need to keep that in mind. Differentiating the left side is just simply dv dt. Differentiating the right side is 144 pi dh dt. Okay. Now, the question is, we want dh dt at t equals 8, and we want dv dt at t equals 8, right? At this moment, it seems like both of those are unknown, but let's look back at the problem. And it says that during the time interval from 0 to 12, water is pumped into the pool at a rate, P of T, cubic feet per hour. And water is leaking from the pool at a rate, R of T, cubic feet per hour. So if we think about the pool as being like a pile of water, and I know it's strange to think of it as a pile of water. I like doing this because, frankly, if you just think of all these problems as like piles of something, in my mind, it makes things a little bit easier. So let's say we have a pile of water here. There's some rate in, which is, I believe they said P of T. Yeah. Right. So if we ignore rate out for a moment, the longer time goes on, since there's some rate of water going into the pile of water, and this can be thought of as the volume, of course, the volume of water. This pile would increase in size if we just were pumping water in, right? But of course, that's not the case. There's a rate out, which we are calling R of T. And so the rate that this pile of water is changing depends on both the rate in and the rate out. So if the rate out were to be ignored for a moment, then the pile of water is changing at exactly whatever the rate in is. If the rate in were to be ignored, then the pile of water would be changing at exactly what the rate out is. But since both are occurring, the rate of change in volume is going to be equal to the rate in minus the rate out. Okay, so at any time t, the rate of change in volume will be P of t minus R of t, the difference in the rate in and the rate out. That being said, if we want dV dt evaluated at t equals 8, we just need P of 8 minus R of 8. All right, and that's the calculator problem. So we just plug 8 into our calculator for these two functions. And P of 8 is given in the table, but R of 8, we would use our calculator, and we would get dV dt. So I'm just going to pause it and calculate those numbers. Give me one moment. Okay, so P of 8 minus R of 8 is 60 minus 16.758. By the way, a few of you asked what you should round to, and as I've been saying all year, round to 3 decimal places. I've definitely said that dozens of times, so it still holds true. The AP is strict about it, round to at least 3 decimal places. So anyway, going back up here, dV dt will equal 43.242. Let's make sure we get the correct units. We're talking about feet cubed per hour. Okay, so this would be your dV dt final answer. And we're going to use that now in this equation over here. Of course, this is dV dt at t equals 8. So we're going to use that here in this equation. 43.242 is equal to 144 pi times dH dt. This is the second part of the problem that we're interested in. And solving this equation gets you, I'm going to pause for one moment. Okay, it gets you a numerical value of 0.096. What are those units? Well, height is a one-dimensional unit. And so in this case, it would be measured in feet per hour. All right, and that would be all. One thing I wanted to mention, when you're solving this piece on your calculator, and you do 43.242 divided by 144 pi, make sure to put that expression 144 pi in parentheses. If you don't, the calculator will read it as you multiplying the entire fraction by pi. So just be careful about that. All right. Okay, here we go. Let's move on to problem number 2. So we have a pipe that can hold 50 cubic feet of water before overflowing. So this is the magic number here. If the pipe exceeds 50 cubic feet of water, any bit of excess, then the pipe will be overflowing, okay? It says that for t greater than 8, the water continues to flow in and out of the pipe at these given rates. So let's see, what do we have here? So we have rate in given by this function, and we have a rate out given by this function. Okay, and we're told that at the very start, there are already 30 cubic feet of water in the pipe at time t equals 0. So what we're interested in is, like, when will the pipe or the amount of water in the pipe hit 50 cubic feet? All right, so first of all, let's get an expression that represents the amount of water in the pipe at any given time. All right, so hopefully we are aware of how to approach this at this point. We need to take the initial amount of water. We need to add to it the rate in, or the integral of the rate in, I should say, which will give you the net change in water pumped in. And then we need to subtract the rate out because this will give you the net change in water pumped out or dripped out, whatever the verb is. All right, so this would be the expression for amount of water at any time t. Let's just plug in the known value, which is a of 0, which is 30. And since both of these integrands have the same limits of integration, we can actually just write them as one integral. All right, and this expression will give you the amount of water in that pipe at any given time t. The question is, when is a of t equal to 50? Because it is at that instant that the pipe will just begin to overflow. It won't quite overflow yet, but at that instant, it is right on the cusp of overflowing. And so that's the time period we're interested in. And so all we're going to do is take our 30 plus the integral from 0 to t of r of t minus d big D of t dt. We're going to take that expression and we're going to set it equal to 50. And there you have it. That's your final answer. That answers the question of, or that satisfies the task of writing but not solving an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, so they want time w, so your upper limit of integration can just be w. All right, folks, there you have it. Hope this made sense. If you have questions about the other parts, don't hesitate to ask. But I didn't really see too many questions that were not answered in the question stream. And to be sure, even people that asked about 1D and 2D, those questions were answered pretty well. I just wanted to kind of explicitly show the work for those two problems. All right. Be well, ladies and gentlemen. Bye.